Well, hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. If you step on inside here, we are going to do an overview of everything circles-based that I've been able to cover, and then some. Not the graphing equations of circles, not the ones with conic sections and parabolas. That's in a different realm and different basis. No, I'm talking about the circle stuff where we have chords, secant lines, tangent lines, circumscribed angles, inscribed angles, central angles, and on top of that we're going to be looking at some things involving circumference of circle and arc length, and area of circle and sector. Area of sector as well, sector of a circle. I didn't do a video on area of sector or arc length, however I might have some old videos that do cover that, as well as areas of segments within circles, which is not what we're covering here, and this does not cover things where chords intersect, where a radius intersects perpendicularly with a chord, or anything of that nature. I will link an older video for you if you're trying to find any of that information, and you can look in the problem set what kinds of problems there are. That being said, we have a bunch of problems here as well, and this is from one of my highly esteemed colleagues here, where they wrote out this stuff. I've not done this review yet, so I like to strategize these kinds of problems with you guys. I believe it's 5 pages in total right here, if you take a look, which has numerous different problem bits. Grab your calculator. I don't have mine with me right now. I'll be fine. Grab your calculator, and away we go. Number 1, for each figure, determine the indicated measures. Here's part A and a circle in the diagram. Note that P is the center. This is otherwise known as circle P. The measure of arc QS, we are going to find out how large this thing is right here by knowledge of the information that we have. Now, what I want to talk about to start with is just these are central angles right here, and these intercepted arcs have the same exact measure. If that's 47 degrees as an angle, then the measure of arc UT is 47 degrees. This is 55 degrees right here. Hey, so this is 55 degrees. If you want to find the measure of arc QS, you can also find, and by the way, we're talking about this arc right here and not this arc right here. This is what's called a major arc. This is what's called a minor arc. You can tell which one's being referred to because 2 letters are being used. If they use 3 letters such as QTS and it had to go through T right there, then it would be a major arc like that. But we're talking about this here. Anyway, the point I wanted to make is if you want to find out this intercepted arc measure, you have one of 2 options. You can either find the central angle measure, and that's the same thing, or use those central angle measures to choose these intercepted arcs. Now, the other bit that we can kind of work out here, we have a vertical angle pair right here. This is 47, this is 47. That could be potentially helpful, but we still need this part. What I'm really looking at right now is the idea that we have a semicircle. We have a semicircle right here, and we know that because this is a diameter right here, because P is the center. That means this entire thing is 180 degrees. 180 degrees. Now, I don't know if I need the 47 specifically for this, but what I do need is this guy just right here, QS, with the knowledge that 55 of the 180 degrees is right there, and so this is what remains. I know I'm kind of saying this in a bunch of different droves, but I'm strategizing with you on how to do this. And don't worry, I'll go faster later. I just want to kind of point out the different things we have. Is the 47 needed? I don't know. Maybe we use it later. But right here, we just need to know that 55, and it says measure of arc QS equals, it's 180 minus measure of arc ST. Arc ST is right here. That's the 55 degree one. This whole thing's a semicircle, so this is going to be 180 minus 55, and that is 125. And make sure you put degrees there, 125 degrees. And like I said, I'll be going faster than that. Now, for the sake of doing a second part, this measure of arc QT, I think it's worth writing down any numbers that you find and use, like the 47. I didn't use the 47 for this problem at all, whether right here or this one, but I'll write it down when I have it. In fact, this whole thing is 125. Well, what's 125 minus 47? That'll give us just measure of arc RS, and that may be helpful for something that we do. So let's look at what measure of arc RS even is. That is, in the future I won't add this unless I really need it. I think that's 78 degrees right there. So we have all these different measures here, and we could even use that, of course, to find measure of arc QU. Now, what's the next one? Measure of arc RQT. We need this guy right here now, measure of arc RQT. Okay, looks like the 78 is actually now useful because what we need to do, we have 2 options. An entire circle's measure is 360 degrees, and we can take 360 and subtract the sum of these two right here. So we could do something like 360 minus the sum of 78 plus 55 degrees right there, which, I don't know, 78 plus 55 is 133. So 360 minus 133, I really probably do need a calculator, which is 2... Why am I so bad at this right now? 227? Please tell me I'm correct on that. I think so. 227 degrees. Let's show you a different version to confirm that I'm correct. And then it's Saturday right now, so it might be a little rusty with my math. So 227 is one version of that option. Again, the whole thing is 360. We take out this part of it. What's another option for this thing? Well, like I said, we could figure out what QU is. I guess this is... okay, yeah, let's do that. We could figure out what QU is instead of saying that this whole thing adds to 360, subtract all these. Remember, we do have some semicircles. So, for example, UQR is a semicircle. So this can be 180 minus 47, which is 133 on its own. So this is 133 degrees right here. So RQT... Oh, I'm sorry. We don't even need that, right? This is a whole semicircle. This is 180 plus 47 right there, which is 227. That would have been probably the faster way to do this one right here. So again, a lot of different ways to do these, and that's the idea. It's kind of nice that I have that plausible deniability. I haven't seen this thing before. I like to work it out with you and show you different ways. I don't think I'll always show you a bunch of different ways unless I already have some of the information readily available for me to use it. And I won't show you a significantly harder way if we already know a significantly easier way. Okay, let's keep moving forward here. We got a lot of problems to do. Part B, we have a brand new circle right here, and we have to find some measures. Now we got to find the measure of an angle. Measure of angle FGI. So what you have right here, this is the angle we're looking for, FGI, and this little guy right here. This is not known as a central angle. This is known as an inscribed angle. An inscribed angle is an angle whose vertex lies on the circle itself, and then you have its endpoints also lie in the circle. And that's important because what we can do is look at its intercepted arc, and unlike that of a central angle, an inscribed angle's measure is actually half of its intercepted arc measure. The measure of angle FGI is half the measure, let me do that again, it's half the measure of arc FI. You take half of FI, half of 18, and you will get your value. That's 9 degrees. An inscribed angle is half the measure of its intercepted arc, and an intercepted arc is therefore double the measure of its inscribed angle. And I'm going to be mentioning both a whole bunch. In fact, it looks like on number 2, or the second part right here, we're going to be doing exactly that. The measure of arc GH right here, we need to find out the intercepted arc measure for this inscribed angle GIH. The measure of arc GH is double that of the measure of angle GIH. So we are going to, and I'm not going to write this kind of thing every time. I'm just giving you the idea of it. So we are going to be doubling 39 degrees, which is 78 degrees. And that's all we have to do for that problem. So I didn't really want to fit the 9 in there, and I don't have to write that anymore. We got the 2 answers we needed. Okay, part C. Excuse me. Wait, what's different for these for each indicated measure? Okay, I see. Different kinds of questions. So the first few questions we're dealing with have to do with inscribed angles and central angles purely. And then we're going to start talking about inscribed quadrilaterals. Okay. All right, part C right here. We have another diameter. J is the center of the circle right here. So it's a diameter that meets these semicircles. We got to solve for A and B. Oh, interesting. We get to use some algebra here. That's cool. This says 15A degrees, and that looks like A squared right there. Let's hope these numbers pan out as planned. Okay, first thing I'm going to do is solve for A with you here. And straight up, I'm going to tell you, and hopefully you can recognize these when you draw them, this is 90 degrees. And not because it looks like it, even though it very much does when I tilt my head. It's not because it looks like it, it's because this is, there are 2 ways we can talk about it. There's the theorem, the idea, the property, that if you have an inscribed angle whose endpoints lie on the diameter of a circle, then it is 90 degrees. But why is that so? Because this inscribed angle is half the measure of its intercepted arc. Its intercepted arc is a semicircle. This is 180 degrees. Well, half of that is 90. This is 90 degrees right there. So automatically, when you have one of those diameter things, I would mark up right angles, whenever you see them. So that makes this thing 90 degrees right here. And with this O diameter, you can call it a hypotenuse as well. That makes this whole thing a right triangle. I think I'm jumping the gun a little bit there, but what I wanted to mention, I actually don't think we need to know that, but that would make that a right triangle if you ever wanted to do something with that. Like, for instance, this plus this is 90 degrees as angles. Anyway, we can solve for A by having it say A equals. I can't do the work I want to do. I'm just going to do it over here. The 90-degree measure is equal to the expression 15A. If you divide both sides by 15, you get A equals 6. So let me write that over here now. A equals 6. And you don't have to put degrees. The degree symbol is already taken care of there. Well, you might want to because this one doesn't have it, so maybe I should. 6 degrees. So A squared, therefore, and why might I want to use the A squared? Because I got to find B. A squared, therefore, is 36 degrees right here. Why is that important? Because B is the intercepted arc measure for that inscribed angle 36. B is double the 36-degree measure, which is 72 degrees. And this time I really do have to put the degree symbol because, why? Because it doesn't have a degree symbol there. So there it is. Okay. All right. Those are some inscribed angle things. Now, I'm sure inscribed angles will come up some more in central angles, but there's the start. For each inscribed quadrilateral, determine the angle measure. Okay. Basic thing I want to just point out here when we start talking about this is that inscribed quadrilaterals are just like quadrilaterals in that their interior angle sum is 360 degrees. There's no change in that. But now, even more so, when you take opposite angles, like this angle and this angle, I don't know why I marked them like that, those are supplementary to each other. Not congruent, but supplementary. They add to 180 degrees. For a very simple reason, this inscribed quadrilateral has this intercepted arc right here. This inscribed angle has this intercepted arc right here. Together, the intercepted arcs add to 360 degrees. And if the inscribed angles are half the measures of their quadrilaterals, then those inscribed angles add to 180, half of 360. So that's just a good old making sense thing right there that we can use to understand why that is. So we're going to determine the angle measure. Well, I don't know what that means for this thing. Maybe they mean find, I'm going to solve for x, not this. Oh, maybe that's what they mean. They mean solve for this x. No, that's unrelated to this x. Okay, this x and this x are unrelated, okay? This is quadrilateral wxyz, and this is x as a variable right here. So solving for this x, I guess we can use it to find this x. They say determine the angle measure, and they don't indicate one. Let me make sure I'm not missing something. Okay. I'm just going to go ahead, guys. I'm going to find each and every angle measure for you so we're not missing anything, and of course, in doing so, we'll solve for the variable. Okay, we don't have an expression for this x right here, which means, and remember, that's not in x, like, hey, that's x. But, so we can't just add all these up to 360. What we should do instead is work on that supplementary bit, like I mentioned before. Take two angles opposite each other that do have expressions, such as angle y and angle w. Add up their expressions, set them equal to 180. 8x plus 21 plus 7x minus 6 equals 180 degrees. And that's enough information for us to be able to get x. Combine the 8x and 7x, we get 15x. Combine the 21 and negative 6, we get 15 there. Subtract 15 and then divide by 15. I think that's 11. Yep. We get x equals 11. Now we can use that to find the measure of each angle. And even if they're asking us to find specifically the angle x, I'll just go ahead and find the other ones for you as well. Measure of angle y is 8 times, hopefully you're okay with me just saying this out loud, 8 times 15, which is 120, plus 21 is 141. You have different ways you can find that W now. You could just do the supplement. It should be 39 degrees. Let's see if that actually does. Oh, wait, hold on a second. Did I say that right? Oh, 8 times 11, not 15. I'm sorry. I just did something wrong. See, that's a good thing I double checked. X is 11. I'm sorry. 8 times 11 plus 21. There it is. So 109 degrees. Measure of angle Y is 109 degrees. Two ways you could find measure of angle W, therefore. You could either plug this in or do 180 minus 109, which should be 71 degrees, or 77 minus 6 is 71 degrees. Measure of angle Z is 110. I feel like I'm doing that wrong. No, that's right. 110 minus 1, which is also 109 degrees. Apparently those are congruent. That must mean measure of angle X is also, therefore, 71 degrees. You have two different ways you can do that. Again, the supplementary bit, these two add to 180. Or all these add to 360. But again, I think it's kind of redundant to use those two because they already add to 180. So these two, that should also be 71 degrees. I don't know if that's really the final bit that we all wanted here, but I'm going to go ahead and give you all of it. All right, part B. Let's do the same thing, only a little bit faster, and not forget our answer for x this time. All right. Once again, N and L are opposite angles of each other in an inscribed quadrilateral. That makes them supplementary. This is only true for inscribed quadrilaterals that we should be making such a statement, not in just every old quadrilateral. All right, that's 2a minus 2, which is 180. Add 2, divide by 2. Whoops. And you get a equals 91. Okay, we're going to use the 91 to find the measure of these angles here. I don't know if my picture's cutting that off. It's not, but it's cutting off the n. So a plus 16. So measure of angle n is 91 plus 16, which is 107. Measure of angle, I'm going to do L first because it should be its supplement. 91 minus 18, plus 16, right? Minus 18 is 73, degrees. Those add to 180, that's good. Measure of angle M is 91 plus 30, which is 121 degrees. And measure of angle K, it should be the supplement of measure, this is probably being cut off, is measure of angle M, 180 minus 121, which is 59 degrees, right there. So those are all four. If K was what we needed, we got it. Okay, I'm going to go ahead and move forward. Okay, refer to the diagram below. Segment AB is tangent to circle C at point B. They're talking about right here, tangent line. I'll talk about all that in a second. And AD is tangent to circle C at point D. Find the measure of angle ABC. Okay, we got a few things to do. Okay, and I have to remind myself that my picture cuts this part off. It's hard because I don't look at that part on my software. Okay. All right, so first of all, tangent lines. Tangent lines are lines that intersect a circle or a curve at exactly one point. If I extended this further, you can just kind of see that it just kisses the circle at a single point right there and then grazes right off and goes. There are these other ones called secant lines, which I'm sure we're going to refer to at some point. A secant line intersects a circle at 2 points, like so, and that is not what we're talking about. So a couple different ways that we can talk about what it is that we are talking about here. We need to find the measure of angle ABC right here. Now, a tangent line, how do I say this? A tangent line that then has a chord inside your circle creates also some version of an inscribed angle. And I want to make mention of that first. So, for example, not even talking about, we have to find one of those later. Like this part D, angle part C, angle BDA. Not that I'm going to find the measure for you right now, but this is actually an example, I shouldn't use blue, of an inscribed angle. It's weird because it doesn't really look like one, but it's inscribed because, like even right here, its intercepted arc. Its intercepted arc is this guy right here, and its point is on its vertex is on the circle itself. So this inscribed angle is half the measure of its intercepted arc. And I bring about that information for you because what we have for tangent lines in any situation, including with a radius, like this one, a diameter, does mean this is an inscribed angle whose intercepted arc would be this guy. And in this case, this guy is a semicircle. An inscribed angle is half the measure of its intercepted arc. What is half of 180? 90. So measure of angle ABC is 90 degrees. Now, I mentioned that in just also telling you that that's also a theorem and a property, that a radius or a diameter that intersects with a tangent line at that point of tangency right there is intersecting at 90 degrees. That is 90 degrees right there. So you don't have to know the intercepted arc bit of an inscribed angle to get that answer, but we will have to later, and that theorizes as to why that's also true, right? That also tells us how we understand that works. Part B, measure of angle DCB, DCB right here. Well, that's a central angle, if you can see right there. That is a central angle. Now, its intercepted arc is this entire thing right here. We don't know the intercepted arc measure yet, so it looks like we can't really use that. But we do know this 40 degrees outside of that. Why does that matter? Well, by the way, I should also mention this is therefore a right angle too, right? Well, let's check this out and I'm mentioning things in such a way that you can know why it is, as opposed to just hearing it once and then moving on. So let's take a look at what we have right now. You guys see this quadrilateral right here? 1, 2, 3, 4. I have a quadrilateral right here where I know 3 of the angles. Mr. Robinson, you only know 1 angle. Nope, we know 2 others. We know this is 90 and this is 90, right? In this circumscribed angle, an angle whose sides are tangential to the circle right here. In the circumscribed angle right here, 2 of the angles are right angles. They're opposite each other. They are supplementary. In a quadrilateral that adds to 360 degrees, that also means that these 2 are also supplementary. A circumscribed angle is supplementary to its associated central angle. The central angle meets at the points of tangency of the circumscribed angle, like so. That means that 40 plus the measure of angle DCB is 180 degrees. Those opposite angles are supplementary, as those are also both congruent 90-degree angles. I guess that makes us a kite. Subtract 40 degrees, measure of angle DCB is 140 degrees. Okay, so that's 140 degrees right there, which means I'm going to mark that as such. Not just this 140, but if it's a central angle, then its intercepted arc is also 140 right there. All right, measure of angle BDA. Now, this is important that I just got that 140 and that I made mention previously about the whole intercepted arc business. BDA is an inscribed angle. I mentioned this in the beginning. It's an inscribed angle whose angle itself is also one of the endpoints of its intercepted arc. Its intercepted arc is 140 degrees. So measure of angle BDA is half that measure. Half of 140, which is 70 degrees right there. And I don't really know if it's worth drawing that all in. I guess I'll try to. There's a 70. It gets pretty confuzzling. There's a lot of stuff here. Lastly, measure of angle CDB. Where is that? CDB. Oh, that's inside right here. Okay, let's see. So CDB. You have 2 options, one a lot easier than the other. Look, we already know, and again, this is pretty confusing looking right here. Remember, this whole thing is 90. Measure of angle CDA, ADC, right? That's 90 degrees, just like this one was. So the 70-degree angle that I have right here, which is good that I wrote it, 70-degree angle right here, and this little guy right here, they're both complementary to each other. So, it's 90 minus 70. 90 minus 70, which is 20 degrees. I want to make light to another thing that you could do to get that answer, though. I want to show you, if possible, and I'm going to erase pretty much everything but this 140. I erased it, but I'll bring it back. I want to show you something else here. So this is 140 right there. Do you guys know what kind of triangle this thing is? This is an isosceles triangle. I know it's an isosceles triangle because these are radii of your circle, and radii are congruent to each other. Those are congruent. That makes the base angles congruent right here. Whatever this angle is, so is this one. So what would be 140 plus some unknown x and some s? What are those 2 x's if you add them all up and they equal 180? Well, 2x is 140, therefore x, equals 40, therefore x equals 20. So you also get 20 degrees there. They are both 20-degree angles in an isosceles triangle. Like I said, I went against what I said. I said I wasn't going to do anything that was reasonably harder, but maybe I can give use to that later. Or just have you understand kind of how that can also work. Okay, use the diagram below. P is the center. We got to solve for x, and then a bunch of other things. Okay, so this is once again one of those, they don't mention it, but at some point you kind of see and understand how this works. This is a tangent line QM. This is a tangent line QN. This is the center of the circle, as they mentioned. So these are radii that intersect. What does that mean? 90-degree angles here. Whether or not we use that is going to be irrelevant to how I'm going to use this, because we mentioned that a circumscribed angle, opposite its associated central angle, are both supplements of one another. To solve for x, they're definitely not congruent to each other. Just look at them. 2x minus 2 plus 6x minus 10 should equal 180 degrees. 2x plus 6x is 8x. Negative 2 minus 10 is negative 12. Excuse me. And that equals 180. Add 12 to both sides. Divide both sides by 8. 24. Hope I'm right. 24. So x is 24. I don't need degrees for that as far as I'm concerned. All right, measure of angle QMP. Well, I can tell you right now that's 90 degrees. We already brought that out from before. MQN. If we substitute 24 for x, we can figure out that value. So measure of angle MQN is 2 times 24 minus 2, which is 48 minus 2, which is 46 degrees right there. And then measure of angle NPM. NPM is the central angle right here. So you have two options. You can do 180 minus 46, which should be 134. Or we can substitute the 24 into here as well. 6 times 24 minus 10. 6 times 24 is 144. Minus 10 is 134 degrees. Okay, those are the answers right there for number 4, which is more of the circumscribed angle bits. All right, number 5. Now we are talking about some lengths, and this is actually, I'm not going to say opposite. Well, yeah, it's a different order of what I did with my kiddos, because I be sure, if I'm seeing these things right, it looks like we're going kind of in order of how the module really covered information. We start with central angles and central angles and inscribed angles, and then they go to inscribed quadrilaterals and then tangent lines, and we just dealt with some of those. By the way, I didn't see anything on tangent. I want to bring something up here. I didn't see any questions on them yet, or at all, I don't know, but there is something regarding the lengths of tangent lines as well, right here and right here. They are congruent to each other. If I gave y here and I gave 7 and I said solve for y, well, guess what? Y equals 7. The point is you can make equations with those things as well. Anyway, there's a section here that involves tangent lines, which is what you saw in this problem with, of course, circumscribed angles, and in this problem right there, which would bring about those length questions. Maybe they show up. Maybe they show up. But this next question, should I say, section is involving chords which intersect and talk about the lengths that associate with them, possible secant lines and tangent lines that intersect with the circle and how their lengths relate. And then they talk about how their angles relate. So when I did my videos with my kiddos, I started with the angle measures of these. So expect to see some more angle measure questions, and remember how inscribed angles work for me to talk about them. And I'll try and be brief because I've mentioned them before. But let's move forward. Number 5. Use the diagram below right here. And I'm not going to get into the proof stuff other than to mention how it exists, not really prove it. But in order to solve for some of the lengths in here, when two chords, when they intersect, or two secant lines intersect inside of a circle, the chord breaks up into different parts of segments. Like this chord breaks up into x and 8. This chord breaks up into 2 and 4. Now, in order to find these measures, there is a specific relationship among these, which is as straightforward as this. When I multiply this by this, that equals this times this. And it has to do with triangle similarity. I'm sure one of my videos really talk about it in somewhat greater detail. I can't guarantee that. But if you multiply 8 with x, that equals 2 times 4. That part times part equals part times part. Just take my word for it for now. If I need to do some more proof stuff with it, I totally can. 8x equals 8, therefore x equals 1. So that length right there is 1. What's the length of AD? AD is this part plus this part. Don't multiply them. Just 2 plus 4, right? That's 6. The BE is 1 plus 8, which is 9. I never said these chords were equal to each other. I said the products of their broken up parts, the split segments of their parts, are equal to each other. Yes, 1 times 8 equals 2 times 4, and there's a similar triangle aspect to it. And you say, where are the triangles? Well, I could make a triangle right there and right there. Boom, 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 boom. You can do some angle proof to show proportionality and prove all that. But I'm going to leave it at that for now. Okay. Part B. And yeah, this is where we're going to start hitting some of these other bits. So part B, now we have some... okay. Well, okay. Now we have some lengths right here. We could go about some different examples, which could give different kinds of answers. Look, the answer is 4.5. But right here in this particular problem, you have two secant lines intersecting outside of a circle. Now, there's another associated property or theorem that you can use with this one, which the way that I say it to my students goes like this. Here's the outside part of this secant line, or secant segment. Here's the whole part of it. Okay? Here's the outside part of this. Here's the whole. of this. It works as such. Outside times whole equals outside times whole. Again, there's a triangle similarity relationship that we'd all go through. I'm going to leave it at that. And let's try that out. Outside times 5 plus 4.5 whole equals outside times whole, 5 plus x. Now, I will go and say this. This is a little bit of too much to do. Look, this is 5 and 4.5. This is 5 and 4. That's the only way it's going to be outside times whole. The answer is going to be 4.5. But let's, maybe you have to do some quadratic. Well, not this one. But maybe you have to do some extra work and some other times. Maybe it's not that number. Let's see what we would do with this. 5 times 9.5 is 47.5. 5 times 5 is 25, and then plus 5x right there. Subtract 25 from both sides, and you get 22.5. Divide both sides by 5. Well, it better be 4.5. I do believe it is. X is 4.5 right there. All right. The length of BD, all of that is 9.5. That's technically something you had to know leading up to that part of the problem with the outside times whole bit, because that's the whole. And length FD is also 9.5, because this was 4.5 as well. So, a little... Hold on, I'm going to scroll down and see what other kinds of... Okay, we hit sectors. So I want to bring about some other kinds of situations, even though I'm not going to do the problems, but I just want to bring out some other things that we might have to do in these problems here. Look, clearly if this number's a 6, then it's not like this answer is just 3.5, right? You got to actually do the solving stuff. Some other properties that can come into play here. It's not just two secant lines that intersect on the outside. I already mentioned what happens when you have two tangent lines that intersect on the outside. You don't have to do that whole property bit because you already know there's equal to each other. So you set them equal. But a third one is tangent line times secant line like this. And what happens right there? Well, you do, if this is A and this is B and this is C, you would do the same thing as with the secant lines here. You would do outside times whole. A is the outside of this tangent line, and A is also the whole tangent line. There's outside times whole equals, I gotta sneeze. Excuse me, equals outside B times whole B plus C. I don't want you to try and memorize a formula here. What I'm saying is outside times whole equals outside times whole still exists for tangent and secant line, much like secant line and secant line for outside times whole equals outside times whole. So that still applies there. Now there's no problem that is being used in this situation right here for me to mention more of that, but there it is. Okay, I talked about this stuff before, and it looks like it's kind of showing up right here where we have these inscribed angles. Make no mistake, you are looking at inscribed angles when a tangent line intersects with a chord. This is an inscribed angle whose intercepted arc is this whole guy right here. And then over here, you have an inscribed angle right there whose intercepted arc is this whole guy right here. So we got to find some measures here. We got to find the measure of angle ABE, so that was this one right here. We've got to find this angle when you know its intercepted arc is 128. So we got to take half, right? An inscribed angle is half the measure of its intercepted arc, which is going to be 64 degrees. The measure of arc CE right here, that is the intercepted arc for this inscribed angle that is 68 degrees. So you are going to double that 68 right here. And that's 136 degrees. And that's all you got to do in the problem. Maybe they asked for this or this later, and you could find that intercepted arc, and this inscribed angle is half of that intercepted arc, and all that jazz. But nonetheless, we move forward. Okay, I think these are the last two, the last two questions before we hit sectors and such. I don't know, maybe they asked for angle stuff later. Like I said, I haven't seen this before. Here's how I've talked about this stuff here, and I'm going to kind of be brief with my conversation on it and see if it makes sense, and I think I got to add some more different kinds of questions with this, not in full, but just the properties and what we do. We got to solve for x here. Now, the way that I've spoken to my students about it right here is, let's say that I took this angle right here and I moved it in such a way that it was treated like an inscribed angle, that I moved it up, 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 and as an inscribed angle, an angle that's on the circle, it now has an intercepted arc of this amount. Well, x, that's still x, right? I just took the angle and moved it. I didn't manipulate the angle itself. I did, however, manipulate its intercepted arc as it's an inscribed angle. Well, this x is half the measure of this intercepted arc right here. if only I knew what this intercepted arc was. Well, do you know how much it is? It is taking, remember, this whole thing was 173. You have to take out how much you lost right here. How much is this? How much was lost right there? Well, it's the same. You see these kind of parallel lines right here. You can see how this is 79 degrees right here. Well, this is also 79 degrees right there. You take out 79 from 173, 173 minus 79, and you get this intercepted arc right there. X is half of that. X is half, and I'm going to erase all this. X is half of 173 minus 79. So let me erase all that and see if this makes sense what you can do with these problems. When two lines, a secant line, tangent line, two secant lines, two tangent lines, when they intersect outside of the circle, you can treat it like an inscribed angle in that it's half the measure of its intercepted arc, parts that are gained and lost. As I back this angle up, you can see how much was gained. You can see how much is introduced right here. Take big minus small, half of big minus small, half of 173 minus 79, and you go to work. We get half of 94, which is 47 degrees. I believe that's it, or 47, I guess. You don't need degrees. So X is half of that right there. Now, the same scenario can be applied here. Ooh. Okay. My students might get lost. Wait, hold on. What do we have to find on this problem? Okay. This problem's missing information. Maybe they're saying find A or something like that. Trying to think how to introduce, because I didn't really talk to my students in this way about this kind of problem. I probably should now. Well, I'll call this A, I'll call this B right here. Let's solve for A and B. And be like, what the heck can you do? Well, I'll tell you what they are. A is 180 plus, oh, whoops. Excuse me, B, let me do this again. B is 180 minus 60, which is 120. And then A is 360 minus 120, which is 240. Oh, yeah, it is 180 plus 60. 180 plus 60, which is 240. I don't really go the properties that way. I should, but it's just one more bit of things that we don't need here. Okay. Y 180 plus Y 180 minus. Well, let's get into the idea. We've seen this property thing here before where we have a center. And as you can tell, these are tangent lines. They'd intersect these 90-degree angles, blah, blah, blah. We get the gist. Well, this 60 right here is supplementary to this central angle right here. That makes this 120. If this is 120, then B is 120. Basically, these two are supplementary to each other. So, therefore, is the associated central angle's intercepted arc. That's why that's 180 minus 60. Why 180 plus 60 right here? Well, you need the other portion of the intercepted arc bit. Like I said, this is also 360 minus 120, which is 240 right there. The 240 is also 180 plus 60. I feel like I have to sneeze again. Anyway, so the aspect right there, that's what we're solving for. It's kind of missing information, but those are the two arcs right there. Now, what I want to make mention of right here is you can still apply the same thing that I just did before. Let's say we had another bit of information. I don't want to stay completely in the dark here. Let's say we knew that this was 240. We knew that straight up. You can still do your 180 minus 60 is 120. I get it. I just want to go to the thing that we just said before right here. You can treat, once again, this 60-degree thing as an inscribed angle whose intercepted arc, if I slide this thing up, its intercepted arc is double that of the inscribed angle, right? If I move the inscribed angle all the way up here, say, for example, its intercepted arc should be double that. So that should be like 120 degrees, for example. Now, the idea here is, once again, it's half of the big guy minus the small guy. 60 is half of 240 minus B. If I double both sides, I double the 60. 120 is 240 minus B. Add B to both sides, subtract 120 from both sides. B is still 120 degrees. So a bunch of different ways you can go ahead and do that right there. This is 120. This is 240. I just wanted to bring that about. Last thing I want to bring about before we move forward into sectors and things like that is if you have two chords intersecting inside of a circle, boom and boom. If you have two chords intersecting inside of a circle and you have some angle you're trying to find here and you have some A and B, before we talked about an angle intersecting outside is half the difference of those two arcs right there. Well, this one you could treat as an inscribed angle if you back it up onto onto the circle, and it becomes half of the sum of these two arcs right there. That x is half of the sum of a plus b. And it seems we didn't get a question like that on here. We had a length-based question on here, but not one of these. So, it's half the sum instead of half the difference. I do have some other videos that do bring it up. I think I even get to the proof basis as to why, not proof, but the idea as to why that is. I really like to treat these like the inscribed angle bits, that they can be considered. And I think that really helps. And by the way, if this is x, then so is this right here. They're vertical angles. So the way I mention it is it's like half the intercepted arc and its vertical angle pair. Half the sum of both of those. Okay, we are doing some things with arcs still. That's good. Just a little bit here and there. Because find the... Oh, no, we're not. It says find the length of, not find the measure. Oh, yeah, this does right here. Okay, so we might do a few here and there. But now we're going to talk more about sectors, arc length, circumference, area, things of that nature. All right, P. Circle P is the center of a circle with radius 15 centimeters. So the 15 is just this, not the whole diameter. There's your 15. Find the circumference of circle P. Okay, your circumference formula is, you have 2 pi r, 2 times pi times your radius, or diameter times pi. And you know what? I do need a calculator, because if I'm going to be rounding some answers to the nearest tenth or something like that, let me bring up my one on my computer. If I'm going to be doing something like that as needed, I should use this calculator here for that. I'm going to give you exact answers in terms of pi whenever, and then I'm also going to be rounding for you and show you those examples. So I do have a calculator now here, just in case I do need it. Okay, so here we go. Circumference is 2 pi r, or diameter times pi, because of course diameter is 2 times your radius right there. Either or, when we find the circumference of circle P right here, this is going to be, it's not much room, let's see, equals 2 pi times your radius of 15, which is 30 pi centimeters. That is an exact answer right there. That's in terms of pi. If we, and it doesn't state to, but if we round it to the nearest tenth, which is something we've been doing with my kiddos here, pi is about 3.14, but I'm not going to be using an approximation. I'll be using as exact as I can before I am done rounding here. So 30 pi, 94.2477. I'm just going to say 94.2 centimeters. 94.2 centimeters right there. Now, in terms of pi, that is 30 pi exactly. When you multiply by pi, you get kind of the clearer version of the number, even though it's rounded. Find the area of circle P. Now, the area of a circle is pi r squared. You take the radius and you square it, and you multiply by pi. So you can see where I'm going to have answers in terms of pi, and then I will, of course, round to the nearest tenth as well. So the area for this one, you take pi times 15 squared. So area equals pi times 15 squared, which is 225 pi square centimeters. You want to leave those units there, and that is an exact value there. 225 pi, and I'm going to go to my calculator here, take my word for it. I'm getting 706.85. So 706.9 square centimeters approximately. Sorry about the room. Yeah, room's going to be a bit of a trouble. We have some other problems to kind of deal with here, so I might have to work it out on the side. All right, part C. Find the length of AC. There we go. Okay. Find the length of AC. We have to find this length right here. Notice they did not say the arc measure. However, I will also give you the arc measure because I'm going to use that to answer the question. So here's the idea. Let's get its arc measure first. This is a semicircle. This is 180 degrees. That's 105. This is 180 minus 105. That makes this 75. This is 75 degrees right here. That means its intercepted arc measure is also 75. We know the circumference of the circle, and we know the exact one. It's 30 pi. 30 pi is the distance around the entire thing. We want to know the distance of just this part. This part is just a fraction of your circumference. What fraction? Well, what's 75 out of 360? Why am I saying 360? Because the whole circle is 360. If the whole circumference is 30 pi, and the whole measure of your circle is 360, those are equivalent. So whatever 75 degrees is out of 360, so is this arc length out of 30 pi. I like to set it up as a proportion for my kiddos, but you can also, of course, multiply by that ratio, by that 75 over 360 ratio. But that's exactly what I'm going to do. Whatever 75 over 360 is, so is the length of arc AC over 30 pi. 30 pi is circumference of the whole circle. This is arc length. This is degrees and degrees. Eventually, you're going to multiply 30. If I multiply both sides by 30 pi, basically you're doing AC is 75 over 360 times 30 pi. Now, I'm going to reduce some stuff. The easier reduction I actually see in front of me right now is 30 over 360. I know that's 1/12. So 1/12. And 75 over 12, those can both divide by 3 at least, and that's 25 over 4. So AC is 25 pi over 4 centimeters. That's an exact value, or 6.25 pi centimeters would be an exact value. So there's the length of AC in an exact way, 25 pi over 4 centimeters. As an approximation for you guys, 6.25 pi, it's around 20 something? 19.6 centimeters there. Okay, sorry for the room again. So again, you're taking whatever fraction out of 360 your arc is that you're finding its length of compared to that of the circumference. Find the area of sector CPB. Okay, so just the shaded thing. I was like, that's an angle. So we want to find the area, the shaded region right here. Area sector works the same way as arc length does. This is a fraction of your circle. This is a piece of your pi. Let's say this was a third of your pi. Because if it was 120 degrees, it's not really. Well, let's say this was a third of your pi. This would be a third of your area. Straightforward. So whatever 105 is out of 360, because it's a central angle. So it's whatever 105 is out of 360, your sector is the same amount out of your area. Okay, so we can set up another. I don't know where I can benefit the room here. I'm just going to write it down below and erase it later. So whatever 105 is out of 360, did we get area? We did, 225, right? The area of sector CPB, I'm just going to write CPB. CPB is out of 225 pi. Yeah, that's a lot there. So CPB, we have to take 105 out of 360 and multiply that by 225 pi. Now I know 225 pi is 5/8 of 360. So boom, boom, 5 and 8. And that might be all I can do to reduce that. So as an exact answer, these aren't the most fun exact answers here, but I'm going to use them. As an exact answer, 525 pi over 8 square centimeters right there, I guess is your exact answer. I don't want to be wrong. I hope I'm right. I'm just going to go ahead and round to the nearest tenth as well here. 525 pi divided by 8, and I'm getting 206. What was 706? Yeah, that's probably right. 206.2 around 2, and I got to write this there in a second. 206.2 square centimeters. To confirm that, I'm going to do, just even though they're rounded, 206.2 divided by 706.9. I'll show you this on the calculator. 206.2 divided by 706.9. And these are rounded. It's around 0.3, right? Well, what's 105 over 360? It's around the same thing, right? So they should be exact. The problem was I rounded, but that kind of confirms to me that they're the same fraction as they should be. Whatever the area of the sector is out of the whole area, so is 105 out of 360. So at least I trust that I did my numbers math before that right. So as an exact answer here, let me block this off. As an exact answer here, it was 525 pi over 8 square centimeters. And as an approximation, it's 206.2 square centimeters. And oh yeah, it is definitely expected that you are simplifying your fractions. I'm not joking. It's definitely expected that you're simplifying your fractions. And you're getting an exact answer in terms of pi unless asked otherwise. Maybe you're able to just round early. Oh, I got to find the measure of arc CAB. Notice that's not the same thing as asking for the length of the thing. We're going back to some central angle biz, intercepted arcs. So the measure of arc CAB right here, I believe that's what they're asking for. Measure of arc CAB right here is the semicircle that is this AB, if you will. Although semicircle should have 3 letters. So 180. And then this is 75 right here. 180 plus 75 is 255 degrees. Now, if you wanted to find its arc length, you take 255 out of 360, and that's equal to your arc length out of 30 pi. Which I'm not going to do, because they didn't ask. All right, number 7. If the circumference of a circle is 22 pi feet, and that's it. They're probably saying find the area. They probably are saying find the area of this shaded region right here. I don't see the information. So yeah, if the circumference of a circle is 22 pi feet, find this. Okay, a lot of things to unpack here. Circumference is 22 pi. Now, circumference is also 2 pi r, right? 22 pi equals 2 pi r. Why am I setting that up? Because I want to find the radius of the circle. If I want to find the area of the sector, then I got to find the area of the circle. To find the area of the circle, I need to find the circle's radius. If I divide both sides by 2 pi right here, I will take what the circumference was. By the way, this was feet. And then I can find r. So my radius is 11. Not 11 pi, just 11. 11 feet. That makes, like this right here is 11 feet, you know? So I can use the 11 feet to find the area of the circle. The area of the circle is pi r squared, pi times 11 squared, which is 121 pi square feet. I have no reason to round this right now. I need to use my exact answer to find the area of the sector. I'll go ahead and round later as need be, but the area is 121. Now to find the area of the sector, what you need to find is what the angle of this, or what the measure of this angle is right here. And that's where the 65 comes in. 65 is indeed an inscribed angle right here, whose intercepted arc is right there. The intercepted arc, this guy in green, that's double 65 degrees, which is 130 degrees. That also makes the central angle 130 degrees. Okay, so 130. So whatever 130 is out of 360, the area of my sector is out of the area of the whole circle. So 130 out of 360 equals, I'm just going to call it x. The area of the sector x out of 121 pi. Now I am going to multiply by 121, but let's just reduce those by dividing by 10. So we're going to take 121. Why don't I just keep the same color? We're going to take 121 pi and multiply it by 13 over 36. Let's reduce, and then we'll round. 121 over 36 can definitely, no, not definitely, no. Can those? I'm going to let my calculator help me, but 121 can't divide by 3. It can only divide by 11, so I think I'm going to use my calculator. 121 times 13 is 1573. So 1573 pi over 36. I don't think those can reduce. Divided by 36. Yeah, it's a weird. Oh, maybe it can. Let's see. Fraction. No, I don't see if it can. So that is an answer in square feet. That is an exact answer as well. Nothing to reduce there. Now I'm going to go ahead and approximate it with you guys right here. 1573 divided by 36 times pi. Approximately 137.3. 137.3 square feet. 137.3. Whoops, that's not a 3.3. Now, it might be worth it to you. Remember my double check before? It might be worth it to you as you're doing that. Maybe don't just blindly trust your answer. Think about how much 130 is out of 360. It's a little more than a third. Well, compare 137.3 to 121 pi. Because you're probably thinking, whoa, this is bigger than this. No. 121 pi is, remember, pi is 3.14. You got to like basically triple this number. So it kind of, I think our answer is going to kind of make sense there. It should be the right answer. See, 121 pi is, this number, 380. So what if you do this number divided by this number? Do you get a little more than a third? Do you get a little more than 0.33, maybe 0.34, 0.35? What is 137.3 divided by, 380.1? Obviously, we're rounding, and it's, we didn't get the other numbers. Oh, 0.36, okay. And 130 over 360. It's going to be pretty much close to the same answer. It's going to be a little bit less, or a little bit more. Yeah, so pretty much the same thing right there. And again, that's because the numbers are rounded. If you want to use the exact answers as well, then you should get the exact same decimal. Just some good double-checking measures. Oh, the questions were right here. Oh, no, I didn't even see that. Okay, my bad. All right, what's the area of the circle? 121. Okay, let's use the rounded one as well. 121 pi square feet, or, I'm sorry about that. What did I say? 380.1 square feet as well. I'm sorry. The area of the sector shown above were either of these. Okay. I'm sorry about that. All right. We still found everything we were looking for. Okay. If the area of the circle below is 130 square meters, find the length of AB. We're going to go on a limb and say this is a center right here. That makes 85 a central angle. So we got to find this length right here based on area. To find area, to find arc length right here, we need to find circumference. To find circumference, we need radius or diameter. I think finding radius would be suitable because we have the area and we can use that. The area of the circle is 130 square meters. Now you have to be careful here because it does not say 130 pi. And I don't know how exact we need to stay for as long as we do. I'm going to stay exact for as long as I do. I'm not going to use 3.14. I'm not going to round early. So please follow my algebra when I do this. So 130 is pi r squared. Okay. I'm going to divide both sides by pi. So we get r squared equals 130 over pi. I'm not rounding that. I'm not going to the calculator right now for that. R is the square root of 130 over pi meters. And I'm going to go ahead and leave it like that. That's exact. It's weird. It's very, very, very weird, but it's exact. 130 itself can't have a square root. Why should I be rounding that? I will tell you what the rounded value is about, but I'm going to use the exact one. Maybe if you want me to type the rounded, write the rounded one as I type, it's 6.43. It's a little less than 6.5 meters. But there's the radius right there. Square root of 130 over pi. Little weird, but there it is. So I'm going to use that to find the circumference of our circle right here. And I'm going to use the circumference of our circle in what we do in proportions. And when it comes to an exact answer, yeah, I think eventually we need to say we got to round our final answer to the nearest tenth. But yeah, here we go. Circumference is 2 pi r. Circumference is 2 pi times root 130 over pi. Root 130 over pi. And I'll tell you what, there's nothing here that we can really simplify. I can't cancel the pi over pi because that's inside a square root. I don't even think 130 can be simplified. It can't. So I'll just leave that right like there right now, and that's in meters. And I'm kind of biting my tongue when I say I want to use exact. I'm fine with it, but I'm sure you get a little lost on the matter here when you see that, and I get it. If you want, again, the rounded version of that, times 2 pi, maybe at this point it's worth using the rounded. It's 40, let me show you, it's 40.418, so around 40.4 meters there. What we got to do is figure out how much 85 is out of 360 and multiply that by this circumference, right? Our proportionality goes as such. 85 over 360 equals the length of arc AB over what this over this the circumference, 2 pi times root 130 over pi. Yeah, not very fun when it comes to, oh, let's get this exact answer, whatever. I'm not going to be simplifying, rationalizing denominators and things like that either. Probably not worth it. But if I multiply both sides by 2 pi here, we're going to get AB, the length of the arc equals, all right, 85 over 360. Let's reduce those right now. Divide them both by 5, I get 17, yeah, 17, right? 17 over 72. Yeah, so 17 over 72 times 2 pi root 130 over pi. At some point, look, I'm going to round my answer anyway, so my reduction practices are probably not worth it. 2 over 72 reduces to 1 over 36. This is where I can lose a crowd. I understand that. Just trust your math. Doesn't make it harder, just because you have more work to do. 17 over 36 times pi, 17 pi over 36 root 130 over pi. Yeah, hey guys, there's an exact answer. It's not a simplified radical answer there of any sort, but there's an exact answer there. Let's go ahead and see what that looks like when I crunch it all in the calculator. I'll type it first, then I'll show you the result, because I want to use this. 17 pi over 36 times the square root of 130 over pi. And I'll see if the answer makes sense here. Okay, I'm getting around 9.54. And I'll tell you what, if we rounded early, then that 9.5 that I'm going to write as an answer might have turned into 9.6. I don't know. You don't know. We don't know. So I'm just going to leave it. It's around, whoops, I just wrote 9.6. It's around 9.5. I see some transformers just, boom, there goes Megatron. Down goes Megatron in the background there. AB is around 9.5 meters there. Does that make sense as an answer? Well, before I stated the circumference was around 40 point something. This is about a quarter of it. 85 is about a quarter of 360, a little less, and this is about a little less than a quarter of that as well, because 90 is a quarter of 360. Totally makes sense as an answer when it comes to the length. And remember, this is 85 degrees as a central angle. I didn't mention this, therefore this is 85 degrees as its intercepted arc. That's why we got to say the 85 out of 360. Because remember, if this was 85 like this, oh, we're not using 85 anymore. We got to double that 85, right? We got to use 170 for that. So it's the intercepted arc measure that you have to use, which was that one. That's why we used it there. Kind of a lot of work on that one there, but that's because I didn't round early. I mean, you still got to do the same work, but I didn't round early, so you get this mess. And of course, I tried to keep it as exact as I could. Do what you got to do. You know what else? I'm going to be a little particular with this right here. I'm going to go ahead and multiply. Let's see, this is root 130 over root pi. Let's multiply by root pi over root pi. So you get a root 130 pi over pi. What this allows me to do is get rid of these pi's here. So a better answer than that, exactly. This is the best answer I can give you. 17 root 130 pi over 36. Oh, that's glorious. Oh, in meters. Meters, of course. That is the best looking answer that you can get. Oh, I know exactly. Oh, that's around 9.5, guys. You know? There it is. Okay. So, there we go. There's an exact and simplified. Here's an approximation. I'm convinced of my result. All right. Last question here. Oh, we do get some other stuff here. Okay. Find measure of angle QCB. Where is that? Okay, that's right here. Measure of angle QCB. We need to find this guy. Okay, so to find this guy right here, we have the intercepted arc up here of 74 degrees for its inscribed angle. This is half of 74, which is 37 degrees. So measure of angle QCB is 37 degrees. Okay, measure of angle ABC. This right here is this inscribed angle. Remember, that is inscribed. Its intercepted arc is right there. We currently do not have the measure of its intercepted arc. However, what we do have is a diameter, which makes this a semicircle, 180, which makes this a semicircle right here. And we already know this part's 74. So this intercepted arc is 180 minus 74. Which is 106. So this guy here is 106 degrees as an intercepted arc for its inscribed angle ABC. So we take half of 106, which is, I'm trying to figure out where that's 6, I guess that's 6 centimeters. Half of 106 centimeters, what was I trying to do? Half of 106, which is 53 degrees. So that angle ABC is 53 degrees. I'll just leave that 106 there and I'm good. Okay, so there's that and there's that. And last question as we are past the hour mark. This did not feel like an hour for me. Last question here, area of circle P. Okay, to get the area of the circle, we need the radius. Now, to get the radius, it would be nice if we got this whole diameter. And we can probably, you can see how the 6 centimeters and 8 centimeters might be used in some case here. So you can tell this is an inscribed angle whose endpoints are on the diameter. What did we mention for that before? That's a right angle. If that's a right angle, that makes this a right triangle. I told you we'd use a right triangle at some point here. This is a right triangle with leg lengths of 6 and 8. So you have options to find the length of QC here. You can say 6 squared plus 8 squared equals QC squared. But we've used Pythagorean triples in the past, and you might know that this is a 3, 4, 5 Pythagorean triple, which means this is a 6, 8, 10. QC equals 10 centimeters thing. We're not done with the answer. You guys do Pythagorean theorem if you don't know what I just did for an answer. But that's 10 as a whole right here. That means the radius, I'm just going to say r, that means the radius is half of 10, 10 over 2, which is 5 centimeters. We use 5 centimeters to find the area, of just the circle. I thought it was going to be a sector. To find the area of the entire circle here. The area is pi times r squared, which is 25 pi square centimeters exactly, and approximated, calculator one more time, 25 pi, it's approximately 78.5 square centimeters. 78.5 square centimeters. Okay, guys, that ought to do it for this one here. Now, there were some question types that were not asked and were not covered. Like I said, I might have to link a couple things down below in the description section. Some certain kinds of problems, if you weren't even trying to find these problems, you're trying to find things where you're graphing circles, and you're trying to find where diameters and radii intersect with chords perpendicularly. They're perpendicular bisectors. I got some old videos for that, like 6-year-old videos or something like that. If you're trying to find some other things that are relevant to this, but you didn't see a question type on it, I'll try and find the link to the video that covers that portion. But you got to know what it is that you're looking for and how I tried to mention some of the properties here. Other than that, I hope that it covered some things greatly. You can see how I left exact answers as long as I could before I rounded and use the calculator there. So that ought to do it for this one, guys. This is Mr. Robinson. Thank you so much for watching, and take care. I will see you in the next one. Bye.